Welcome, everyone. To not waste any time, please give a warm welcome to Claudio.
Hi, thanks for having me today. Welcome, everybody. Thanks to having me today with you. And I want to talk about synthetic insurance data. A brief introduction about me. I'm an actuary that working during the day in an insurance company, and in free time I'm involved in data science activities. There are some in the QR code, but some links to reach me. Okay, the agenda of today is really full. We start with the motivation and we achieve the results. The motivation of this study. Motivation is that I was looking for an insurance use case that would allow me to work with a wide range of generative models. And I thought to work on a synthetic non-life insurance data. So the first issue is that about the scarcity in insurance data and insurance research. But the core issue that is not the lack of data, is a lack of shareable data. So we need a realistic claim history, policy details, and premium data that test to new models and deep learning techniques that require maximum volumes of data. But there are some barriers in the insurance research coming from the most insurance data is confidential and proprietary, so is not accessible for external research. And when it is accessible, there are issues such as bureaucratic process, masking technique that complex the filters, the reshareable of the data. Otherwise, you can use also open resource dataset. There are some open dataset available, but sometimes they lack about the necessary diversity and the volume requires to modeling in a robust way, especially in complex area such as fraud detection and risk. The solution can come with the use of the synthetic data generated by generative models, which provide a quite a good solution with a necessary volume of data records and also respecting the relationship between the data inside. So this allows to rapidly prototype and validate sophisticated models in a safe way before to go into the production. But before to start, have a look about how works a insurance non-life dataset. So at the heart of every non-life insurance policies, there is the risk premium. That there is the crucial element to cover the damage. This premium is not a guess, but is coming from a result of an empirical approach combining two essential statistical components, the frequency and the severity. The frequency measures how often a claim is expected to occur, the number of claims per year, and is modeled usually by the Poisson or negative binomial distributions. The other way, there is the severity that measures how much the average of a claim is expected to cost, how often and is often modeled by the gamma or log norma distribution. And by the multiplication of these two components, we obtain the risk premium. This value is the baseline, is the reference premium, and then can be also further customized for individual policyholder, applying risk factors to reflect their individual risk. So the individual risk profile. So your collective risk can be transformed into a fair, personalized price. For this job, I employed two datasets retrieved from the CAS dataset R package. And one is the first dataset is a house pre-auto, is a car insurance dataset coming from Australia, and is a data frame built by 9 columns and with more than 67,000 rows. The second one is a Swedish motorcycle insurance dataset, also with 9 columns and more than 64,000 records. Both of them have standard variables in the dataset used in insurance, such as exposure, claim number of claims, claim amount, and then also come in common are the gender, vehicle age, and the age of the driver. So to build this synthetic data, I use several modeling and with a twist, with using a variable that I discovered in the first dataset and I reproduced it also in the second dataset. These variables used as a conditional variable in this generative model, and is the claim occurrence, claim OSCC variable, that is a binary indicator of the claim occurrence and plays a crucial role for the high quality of synthetic data, because this variable links the two principal outcomes. The claim, when the claim of CC is equal to 0, you have the 0 claim frequency, so no claims, and 0 claim severity, so your damage is equal to 0. Meanwhile, claim of CC is equal to 1, so the event happens, so you have a positive claim event, and you have a number of claim and a claim amount, positive claim amount. So modeling this conditional variable, you are able to respect the imbalance among the insurance dataset, separating array claim event with from the common non-claim event, because insurance datasets are typically known as a rare event, so as imbalanced for this reason. These strategies also enhance the model stability and improve the overall quality of the synthetic data through the conditional variable. Okay, before to start to look about speak about the model, also is important that okay, I can take this I take this two data set and I apply the model to generate synthetic data set to reproduce this data set. But how to validate my synthetic data? I've thought about 3 trials. The first one is the baseline to evaluate the quality assessment by splitting the dataset into the train and test set. So about the classical 80% for train and 20% for test set. Why this? I thought on this type of baseline performance, because when I reproduce the dataset, the synthetic data, I want to understand if this dataset can be employed into the pricing, non-life insurance pricing. So applying evaluating the performance with the generalized linear model, that is a machine learning model we used by actuary for the pricing. The second trial is a little hard because I thought, okay, I reproduce entirely the train set and then I use it to predict the train and the test set. But what happens if instead of to feed all the train set into the model, I use a restricted number of rows and I ask to produce the same number of rows of the train set. So I use the 60% training of the data into the generative model, and I ask to the model to generate 80% to use then for the predictive modeling. And to evaluate if there is investigating whether significant data augmentation can be achieved while maintaining both statistical fidelity between variables and predictive performance. And also it's important to take care about the fairness. So I masked one variable, the gender variable, and I trained the model with this masked variable to look about also the same to look about if I have the same accuracy, the same performance with the insurance synthetic dataset. Okay, now we can start with the models inside. Okay, the first one is used as a benchmark is the conditional Gaussian mixture model. We speak about the Gaussian mixture model that usually we think about this type of model as used in the clustering. Think about the Gaussian mixture model as a party where people are chatting in small groups, each with its own vibe. Some are loud, another energetic, others quiet or thoughtful, but from distance you perceive that the room sounds like a single hum of a conversation. But as you get closer, you realize it's actually a blend of distinct voices. A Gaussian mixture model works in the same manner. So it assumes that the complex data distributions can be composed by several simpler overlapping distribution, each one modeled by Gaussian distribution. And each component of the Gaussian distribution have this component, the mean vector, so the center of the distribution, the covariance, the spread that spread the shape and orientation of the distribution, the mixing weights, and the coefficient that represent the weights, how much each Gaussian distribution contributes to the overall mixture. So the Gaussian mixture model is trained using the expectation maximization algorithm, an iterative process used for parameter optimization algorithm. And is based start with the initial guess of the model's parameters, then with each step calculate the posterior probability that each data point belongs to the each Gaussian component, and with m step update the model parameters to maximize the likelihood of the observed data. And then this process is repeated until the model converge. So once fitted the observation, the Gaussian mixture model can be used as a generative probabilistic model. And this generative nature of the Gaussian mixture model is a powerful tool for tasks such as anomaly detection, density estimation, and also for unsupervised clustering. So the switch into the conditional Gaussian mixture models happen with the introduction of this variable, the claim OCC. So the claim occurrence that is a binary conditioning variable, 0 with no claim and 1 with claim. And in this way, the model fit separate models from claim or no claim groups, policyholder groups, preserving the original status with the claim occurrence patterns. The second model that I used was the Conditional Variational Autoencoder. So the variational autoencoder, think about a art forge that trying to recreate masterpieces, not by coming them entirely, but understanding the sketch, the essence of the artist's style, and generating new paintings that are similar and can be used belong to the same in the gallery, art gallery. So the variational autoencoder works in the same way. It doesn't just memorize all the data, but try to understand the underlying patterns, the structure of the data, enabling it to generate new realistic variation of your data. So at core, variational autoencoder is based on two components, two neural networks, an encoder and a decoder, linked by a latent space. So the encoder maps the input data into a compact representation, not a single point, but just a probability distribution over the latent space. Usually is used the Gaussian distribution. The model learns the distribution and captures the uncertainty and variability. The other side, there is the decoder that samples from this latent space and tries to rebuild the original input. This probabilistic formulation allows then the model to generate different outputs just with the interpolation of the data points. The variational autoencoder is use a loss function based on two steps, split into two components. The first one is the reconstruction loss that evaluate how close the output is to the original input, and the Kullback label divergence that encourage the latent space to follow the Gaussian distribution, ensuring that smoothness continuity in the latent space. Also here, there is the claim occurrence, that is the binary condition input that learns the claim-dependent latent structure, enabling the decoder to generate new synthetic samples consistent with the status claim. Now, there is a little variation of the variation autoencoder. I added the Transformer Decoder. So you imagine that you are a novelist that want to write a story. Then you first draft a rough outline before writing the whole of the story. But this outline is compressed is an abstract, capturing the essential sketch of the story before to create the narrative. The variation autoencoder works in the same way as we seen before, but if you add the Transformer Decoder, you can think about a higher masterclass that is able to turn your outline into a rich story. So the Transformer Decoder uses the attention mechanism to model complex dependence on the data. So in this way, can be considered as a conditional variation autoencoder with a transformer-based decoder as a blending of two models, a probabilistic reasoning and a deep contextual understanding. Another model is the conditional diffusion model. So when you say about the diffusion model, think about that trying to restore a fog about a picture. So take first a clear image, then gradually add the fog, a layer of fogs, noise, until it's completely obscured. Then try to reverse this process step by step, removing the fog and rediscovering the original image. This is the essence of the diffusion model. So start with adding noise, the pure noise, and learns how to denoise this into a coherent, into a high quality output of data. So the architecture is based on the reverse, the forward process that gradually added this noise, and the reverse process that learns to remove this noise step by step using a UNet, a neural network that predicts the noise at each step. And also the score function that estimates the gradient of the data distribution with respect to the noise and drive the model into the direct direction during the noising. So it can be considered an iterative and probabilistic process, and the quality of the refinement gives the diffusion models such as the popularity in dull here and stable diffusion. And also here there is the claim occurrence that a binary condition that ensuring that the synthetic sample maintain logical consistent with the claim and non-claim structure. At the end, I use the large language models. Okay, large language models we know because from the ChatGPT we have a good know about large language models, so it's quite I go fastly. The large language model can be taught as a big library, for instance, when you have inside an expert librarian. The library contains 1 billion books. You and the librarian know the pattern inside the library. And no, it's not memorize every book, but when you ask a question, the librarian doesn't fetch a single book, but compose a new answer by the converging, blending all together patterns learned from across the library. And so the LLM can be considered a statistical pattern finder that generate human-like text, predicting what words should come next based on the training dataset. Okay, the core function, so how it works, start with the tokenization, so convert the words into numbers that can be understood by the machine. This numerical representation then transform into dense vector by the token embeddings. Then map each token to vector space. And then to capture the ordering of the word is used the positional embedding, and the meaningful impact is coming from the self-attention, that the mechanism that assign weights to every word relative to each other into a point, allowing the model to understand the complex context. At this point, there is the feed-forward network that predicts the following words and with the score, and the software max layer convert the score into the probability, and then the tokenization that convert the token into word, into a human readable word. How I use the large language models in my experiment? In an easy way, I use the platform ChatGPT with the GPT 5.1 that recent, and to generate the synthetic data using the prompt. We detail prompt with the distribution data, describing some relationship between variables, and providing also few records example. Okay, now after this model, it's important to consider the validation. About the first step is evaluate the consistency of the records produced, respecting the business logic. So if a claim exists, then a claim amount and claim occurrence must also be positive. Otherwise, all the three variable claim, number of claims, claim occurrences, and claim amount are equal to 0. So this check identify records that in which the models failed to learn these dependencies, thereby ensuring data quality. The second step was a statistical test using the Kolmogorov-Smirnov test. Is a non-parametric statistical test that measures the distance between the cumulative distribution function of the two datasets. A high pi value greater than 5% indicates that the two distributions are statistically similar. And then the data visualization with a univariate data analysis to validate synthetic data. So looking about the alignment between the single feature between real and synthetic data, you can see that the result from the conditional variational autoencoder. You see from about the with red the synthetic data and the blue the real data. Okay, we can see that from claim occurrence there is the pattern as quite the same, are the same also for the gender, for a vehicle age, and is close about the claim number of claims and claim amount, but there is some estimation. Then also the correlation matrix is important because assess the structure, fidelity, the relationship between the variables. So looking about the how the correlation matrix is similar to these two datasets. And also I used the principal component analysis and the UMAP, so the algorithm to reduce the data. I use the principal component analysis to understand the synthetic relations, the linear relationship between data. And you can see that there is overlapping between real data and synthetic data. Also, I used the UMAP to evaluate about the topological structure of the original data. And also here there is overlapping, but I haven't found much more good in understanding the relationship between variables. Now there is about the predictive modeling, so the results that I obtain from the use of this data set. These two datasets. This is the evaluation matrix about from the use of the conditional variational autoencoder. Then we go into the demo app, and I use the GLM to generate both on the real and the synthetic data. So there is the performance evaluated from the frequency model with the mean Poisson deviance (MPD), and also the performance evaluated by the mean gamma deviance (MGD). And we can see that, for instance, this is okay. The test set is good, but the evaluation, the performance of the train is really good because it's under the train set of the original, but they create the overfitting. Also, looking about the second data set, there is some overfitting. Okay, now we go also to about the feature importance to ensure that the model robustness and the generalization about the performance, also about the features used in the prediction, important in the prediction. Also, there is a result coming from the conditional variational autoencoder. You can see that for the claim frequency model, the claim occurrence is in both. The second, also the vehicle value, is different because in the original data they use the vehicle value, instead the second is the vehicle age. About the severity model, there is a completely change. Drive age is in the synthetic data, instead the vehicle body is important in the original data. Now, before to look about the overall result, I just want to share with you the demo app just with Streamlit, and they publish in the next 8 days. And this is an app by Streamlit, is running locally. There is different trials, trial 1, trial 2, the trial 3 I haven't uploaded next days. Just we see the conditional Gaussian Mixture model that I think that is one of the best model that I like it. So the check on consistency, so there is no number of inconsistent data in the first data set. There is, for instance, the univariate data analysis, and that is quite good following some variable, as, for instance, the claim occurrences, the vehicle value, also the claim number of claims, and also the claim amount. Now, about the correlation matrix, a little different. Interesting about the Kolmogorov Smirnov test, because we have then vehicle age, vehicle body, gender, claim occurrences, number of claims that are really similar. I jump the UMAP and the PCA comparison, and I look about, for instance, the second data set, where also here we have the consistency good. The univariate distribution, we say that the model captured the claim amount, claim OC, claim number of claims, and gender in good way. Here the correlation matrix is really good, are similar in the color and in the coefficient. Here also the Smirnov test is quite good with the gender, claim number of claims, claim amount of claim OCC that are really similar. At the end, I want to share about the performance. Okay, this is the performance. About the synthetic dataset is similar of the original dataset, and quite similar also the synthetic dataset, the second synthetic dataset. Okay, also the LLM, we reach good also results here about the exposure, for instance. Not so good about, for instance, in the drive age or vehicle age variables, but the correlation matrix is really similar in the first dataset. Less variable about gender, claim OCC, and claim number of claims are similar. Also about the, I jump over the features importance because I watch that sometimes are changing. I go also about the consistency is good also here. Good the comparison of vehicle age, and also the claim amount, the claim number of claims, the claim OCC. And the correlation matrix is really good. I discovered that the large language models respect the correlation matrix, but in different trials. And here also the Smirnov test, these many variables are similar. And looking about the performance, we can say that the first dataset is really good in the performance, and quite good also is also the second dataset, the synthetic, is respect to the performance of the original dataset. I come back to the slide to end and say that in the overall I focused on the performance. That I had done a lot of validation tests, but just focus on the predictive modeling and to look about the correlation matrix or the Smirnov test about the preserving of the statistical properties. I liked as I understood that the conditional Gaussian mixture models, the large language models, and also the conditional diffusion model. The conditional variational encoders, and also with the variation with the transformers, tend to is good. All models are good in the train set, but tend to overfit. And with the other two trials, there is a little degradation in performance, but in some cases they are acceptable. At the end, just to conclude, I want to say that the conditional Gaussian mixed model, for my opinion, is a good competitive generative model that is used as a generative as a benchmark, and is good for tabular data. And I think that is good compromise between the easy to use and in the modeling and the effectiveness about the performance. Large language models are promising because the synthetic data generation and given by their performance is good, and also are easy to use. You need to keep by detailed prompt, but you have to have a good data analysis of your data, so to write a good prompt. Conditional diffusion models, yes, is competitive in performance, but require a lot of computational effort and also coding effort, because it is really hard to code this type of model. This is some reference, and okay, here. I'm happy to reply to your questions. Thank you.
Thank you, Claudio, for this amazing presentation. We do have quite a few questions, and we
Okay.
are
Wow.
unfortunately out of
Wow.
time.
Yeah.
So, attendees, we can continue this
Okay,
conversation
one and say that no, it's not possible.
mhm, on
How we can
Discord.
decoration matrix be better than vertical differential? Okay, is I think that both are need to watch because the universal because at the beginning when I model the data set, the insurance data set, I look about the univariate analysis, but it's important to decoration matrix because the relationship between variables and the prediction is the result from this correlation, this relationship between variables.
Okay.
Okay.
And Claudio, we'll have to wrap up to start our next session, but I think they're asking about the slide deck. Do you have the link for that?
uh, mm, Sorry,
Or
and the link for I go to the backstage. No.
I think they're asking for your presentation.
Ah, the presentation is
Mhm.
I share the GitHub repository that I put the presentation.
Okay.
Okay. Uh, okay.
All right. So
Okay.
we'll end this session. Thank you all so much for joining. And again, we can continue the conversation on Discord or in the lobby.
Okay.
Thank you.
Okay.